Okay, we've got another data set question here. We're measuring resistance versus length of a wire. I'm going to find the mathematical relationship. So looking at the graph, the line of linear trend line is a good fit to our data. So we can say that we have a linear relationship. Length, resistance is proportional to length. Now, there is the question of the y-intercept. If you look at the y-intercept values, they span a large range from -4 to +2.5. So saying a y-intercept is 0, that's an acceptable result, particularly based on our knowledge that the intercept we have is probably a systematic error. Then we'll trust our gradient works right. So again, R is proportional to L, and in fact R is equal to the slope of the line of best fit, which is 29.7 times L. Now the uncertainty in the slope comes from the uncertainty in the max and min line. Do a normal thing, we take the max slope, subtract the min slope, divide by 2. Actually we have a little plus or minus on that equation, but that's okay. Taking those numbers, we get our slope uncertainty to be 6.25 ohms. Units should be ohms per meter, but that's probably here. Now turning our y-intercept, again take our max and our min. Quite a large uncertainty, as we mentioned. Divide that by 2, and we will get our value being about 3.25. So we want to calculate the resistivity of a wire. So a formula you might recall. Actually, let's write out our formula for resistivity. Resistance is a function of length, right? Because that's our experimental result. We now want to compare that to our theoretical result, which is that R equals rho L on A. Rho is resistivity, that's what we want. Resistivity times the length of a wire divided by the cross-sectional area of a wire. Get that resistivity, and then we can compare it to the accepted value. Again, looking at the formula theory compared it to experiment, identified that rho over A must be equal to the slope. Calculate our area. We'll assume there's no uncertainty in that. Is something of an approximation, but we're not given any information about that, so what we'll go with. Rho then is our slope, 29.7 times A, the area, we get 1.2 by 10 to the minus 6 ohm meters, which is obviously quite close to the value we want. Now, our uncertainty in resistivity, because of the way it's written, is relative uncertainty in resistivity, so relative uncertainty in the slope, which we can calculate. It's about 12%. So our absolute uncertainty and resistivity will be 2.5 by 10 minus 7 ohm meters. Right, so we can state our value for resistivity now. Right, we could be a little more careful with our significant figures and round off where we well, probably, but that's not a super important right now. The important thing to state here is that the accepted value is within that uncertainty bound, right? And we calculate the error in our result by taking our observed value, subtracting away our accepted value. 1.2 by 10 to the minus 6 minus the 1.15 by 10 to the minus 6, 0.05 by 10 to the minus 6. So that's less for nothing, and I'm switching to a percentage uncertainty as well. Well, we take our absolute uncertainty divided by our accepted value times 100%, and we get 4.3%. And so as I said, the accepted value is within our experimental bounds based on our uncertainty estimate for the measured resistivity. Alright, so I hope that helped you see how I would do some of these questions, which will help you do these similar questions. Thanks.